This is lesson 21, which is VHDL example 9. In this example, we'll design a quad 2-to-1 MUX. Now you remember that a quad 2-to-1 MUX we can make from 4 regular 2-to-1 MUXes, as shown here. And you remember that the logic equation for each of these 2-to-1 MUXes is just y is a and not s0 or b and s0. So the question is, we wrote a logic equation for each one of these. So the question is, can we write a single logic equation in which the y's, the a's, and the b's are 3 down to zeros? Well, the answer is yes, if you follow one little trick we have to do. And this shows you how to do it. Here, a, b, and y are all 3 down to 0. Well, in VHDL, if we write the logic equation y is not s and a or s and b, like you might think you could do, it turns out that the arrays have to be the same. So we really can't just use s here. We have to define a signal s4, which is also 3 down to 0. And then we'll concatenate 4 s's together. This ampersand symbol means concatenation. So s4 is just s3, s2, s1, s0. And each of those bits is just whatever s is, this input s, 0, 1. So we got s, 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 s. So this is a 3 down to 0. And now we use the s4 in here. So this single logic equation will expand into 4 logic equations, namely y3 is not s3, which is just s and a3, or s and b3. And similarly, y2, y1, y0 will be not s and a0 or s and b0. So this is a little trick you have to remember. So that will work. The easiest way to do it, however, is to use the if statement that we had for a 2-to-1 MUX. And if you remember, this is exactly the if statement we had for the 2-to-1 MUX. If s is 0, then y is a, else y is b. But in that case, a, b, s, and y were all just of standard logic. Well, if we just change a, b, and y to standard logic 3 down to 0, this becomes a quad 2-to-1 MUX. And we can just keep s as standard logic here. So if s is 0, this s is 0, then y, this 3 down to 0, gets a 3 down to 0. That means y3 gets a3, y2, a2, y1, a1, y0, a0, and so forth. Same for b. So this is the easiest way to make a quad 2-to-1 MUX. We could also use this conditional assignment statement that we had. Again, a, b, and y are all 3 down to 0. S is standard logic. And we could just write y gets assigned a when s equals 0, else b. So there are 3 different ways to make a quad 2-to-1 MUX. You could simulate any one of them or all of them and you'll get the same result. We could pick a to say 5. You could assign this to the fixed value 16 pound 5. This means hex 16, so it's a hex number 5, hex number a, and s is just a clock 0, 1, 0, 1, and so notice that y is equal to a when s is equal to 0, 5, 5, 5, 5, and y gets b, a, when s is equal to 1, a. So sure enough, this turns out to be a quad 2-to-1 MUX. Okay, to implement this on the FPGA, we need to make a top-level design. We'll use all 8 switches, switches 7 down to 0. We'll use the top 4 switches, connect those to B, say, and the lower 4 switches will be A. S will be button 0, so remember we have to put 0 down to 0 because in the UCF file this is a standard logic vector. And we'll use the 4 rightmost LEDs, LD 3 down to 0 for the output Y. We'll use MUX2 4B, this is the one with the if statement, for our quad 2-to-1 MUX, and then we'll just port map it up, and A, which is 3 down to 0, will get connected to switch 3 down to 0. Notice that switch is 7 down to 0. I'm going to pick off the lower 4, switch 3 down to 0 to connect to A. Switch 7 down to 4 will connect to B. The switch will connect to button 0, and Y, which is already 3 down to 0, will get connected to LD, which is 3 down to 0. So this is the complete top-level design. You can go ahead and implement this and download it to the FPGA, and if you're not pushing button 0, then the rightmost 4 LEDs should be whatever the lower 4 switches are. If you do press button 0, then the rightmost LEDs should be the same as the leftmost 4 switches B.